So I have just observed that some detail is missing. My name. I have forgotten to add it. It's not that I am ashamed of it, but just it happened. So this is something very old story because I'm an old man. So I don't know if you will find it interesting. Also, it is related to Carroll, but the problem itself is much more related to an old question asked by Zeldovich in 74. So I hope that you will not be upset to come to such an old question. So you see, the problem is that there has been proposed that gravitational waves could possibly be observed by observing what happens to particles which were in a static equilibrium. They were just sitting with no motion. Comes a wave and it displaces this. The question was, how will it be displaced? Now, this is called a memory effect. To have some very intuitive and funny picture, imagine that you want to know if there is a cat in your cellar, or if you have a mice in your cellar. How can you be sure? You put a piece of cheese in the evening, next morning you return, and if it is in the same place, then there came no mice. If it has changed or disappeared, it means that something happened in the meantime. So this was the original story of this memory effect, which is, I don't like very much the word, but it was not me who gave it. So anyway, the problem is what happens to a couple of particles, or at even just one particle, massive particle, when a gravitational wave passes. Now, what we have to keep in mind is that these gravitational waves come from a huge distance, millions, hundreds of millions, billions years of light years, and go through the Earth in a microsecond. So it is a good approximation physically to consider that they are a very short wave region. Otherwise, it is flat before, flat after. In the meantime, something happened. The mice arrives and takes away or what not. So this was the original idea. Now the problem is that these geodesic equations, which are supposed to describe the motion in a gravitational wave, could not be solved for a long time exactly in this situation. Actually, even now, it cannot be solved really exactly, but almost exactly. I will tell you about it. Now, the story is that if you have conserved quantities, you can integrate the equations of motion. Now, for these gravitational waves, it has been known since the late 50s that there is a 5-parameter symmetry group. 3 of them are obvious. Translations and, well, something like, again, associated with the mass. So in some sense, it is also a translation. Or even for gravitational waves, it is a translation along a light-like direction. However, there were 2 more which could not be identified until very, very recently, which is an absurdity. Absurdity because it was actually contained in a hidden paper of Souriau from '73. And you know, Souriau has been the guy who went against the main ideas all the time, using his own notations. And then when he had his result, he hid it. So this result is in a conference proceedings written in French, published by the CNRS in '74, that nobody has ever seen, except for one person. This one person is Christian Duval, who was a very faithful student of Souriau, but who also had a professor called Lévy-Leblond. So he was the only person who knew about this paper, and he managed to link the two stories. For the story, Lévy-Leblond and Souriau were teaching in the same physics department, but they didn't speak to each other too much. So it took quite a couple of years. So this is the background of the story. But what is the main result or the main question discussed in my talk is what Zeldovich and Polnareff told in '74 without knowing anything about the work of Souriau or Lévy-Leblond. You know, this is what has become called the memory effect. It is in this paper published in '74, which is basically a paper on the flyby of two cosmic objects, galaxies or huge neutron stars and so on. So two huge objects in the sky go close to each other, and when they are very close and very big, then there will be a radiation. So this effect has been called since '64 in a conference, flyby. So what Zeldovich and Polnareff wanted to study is how these gravitational waves could be created by flyby. And at the end of their paper, there is a short paragraph that not many people cared about by that time. Even now it is not well known. They thought two non-interacting bodies, the distance should change, and it could be a non-resonance detector. Why a non-resonance detector? Because all this happened after Weber's so-called observation made in '69. Weber pretended to have observed gravitational waves in '69 by some resonance detector. That time, every physicist who had the correct age became enthusiastic about it. And when it was not confirmed, they dropped the topic. For instance, my friend Gary Gibbons and his young supervisor, just 2 years older than he, his name was something like we will see. Anyway, something like Steve Hawking. So they proposed even an experiment. And then they applied for a lot of money to realize the experiment in the basement of Cambridge. They applied for £10,000 and got refused by the SERC. So then they dropped it and became theoreticians. So that's the way it happened. Anyway, the story originally predicted by Zeldovich and Polnareff that once there is this radiation created by the flyby, you will have what I called memory, or people called after the memory effect, the relative distance of two particles which will change, but the distance, not the velocity. So two particles which are at rest before the wave arrives will be displaced, but they will have a zero outgoing velocity, at least up to some vanishingly small contribution. Now, these people continued, this was what they called the displacement effect, which is again the same lesson. If you have the relative velocity close to zero, then the relative distance will not change. So it's just displacing the two particles from here to there with possibly a different distance. So this was what they exacted. Now, this was not really the beginning of the story, but you see, at that time, in the early 70s, communication between the East and the West was not the best. So there were other people who thought about a velocity effect even earlier, so Ehlers and Kund in 62. They thought for basically what is seen at this picture. There are particles at rest because U corresponds to time in some sense. I will explain later. So here they are at rest. They don't move, just time goes away. At the end, they come out with constant velocities, but these constant velocities will not be zero and will not be equal for the particles. So somehow this is the picture which explains what the content of the velocity effect. So you have again the same type of particles. Here something happens, namely a short burst of gravitational wave rearranges the position in this very short period, this microsecond, and before and after the motion is free, but the outgoing velocity is non-zero. So this is the velocity effect. Now later, Braginski and Thorne, you know, Thorne was a student of Wheeler. Wheeler invented the hydrogenic bomb, so he was not so much supposed to travel to Russia. Zeldovich has invented the hydrogenic bomb in Russia, and he was not allowed to travel until the perestroika to the US. But they had this intermediate electron, Thorne, who commuted between the two countries and carried information in both directions. So they introduced the word of memory effect. And then it was velocity-coded memory. So they went on that work and later became something quite appreciated. Now, first of all, how to describe flyby? Well, actually, in this groundbreaking paper Gibbons and Hawking published in 71, they give a full list of what kind of profile could produce this effect. And they have, the simplest one is just a simple Gaussian. The second would be the first derivative of the Gaussian as profile. And they thought this is for flyby. And then they had higher derivatives with gravitational collapse and so on. And it was in 71, but that time it was out of question to observe anything, yet there was no equipment. The original equipment of Weber, which failed, was a cylinder of 3 meters long. So it was hopeless with that technical level. Now there were some theoretical papers, and this picture shows what happens. Here there is down, upwind, and downwind. Here is a wave zone. And this is the flat before zone, and this is the flat after zone. That means the wave proceeds in this direction. It is 0 before, 0 after, in a very short period. It is non-zero. This is the wave zone, where there is something non-flat, non-trivial. And then after zone, because this is after the wave has passed. And this is the before zone, because the wave has not yet arrived. And the question is how to relate the two between, what is the transition between these two flat zones. By the way, I think that these names of after zone and before zone were given by somebody from Vienna who escaped during, just before World War II to Cambridge. And so it has some local origin here. According to my friend Gibbons, it is not in English, but well. Okay, so now how to describe geodesics in such gravitational waves? And there is a paper written by Brinkmann in 25, very early. And it is, the paper is written on how look gravitational waves, completely hypothetical at the time, so mathematically defined gravitational waves, which carry some covariantly constant vector into a covariantly constant vector. So some conformally related metrics, class of metrics. Anyway, the origin goes beyond our time, which is very short now. So here you have the metric, a flat space. U and V are light cone coordinates, so Z plus D, Z minus D for relativist. And here you have a potential term which looks like a harmonic oscillator up to some details. First of all, here there is a minus instead of having plus. Why? Because the vacuum-Einstein equations require that the Laplacian of these two be 0. So you cannot have with a plus. It is not a harmonic oscillator. There are two harmonic oscillators in the two sectors, say x1 and x2, which one of them is attractive, the other is repulsive. And you can have also such a cross term that I will neglect. It can be treated, but well, it is not in such a short time. So I will restrict attention at this case when there is just here some U-dependent coefficient, which for the moment can be anything, and there is no cross term. A sandwich wave is something where this profile is very short. It is 0 in the before and the after zone, and only it is a wave zone, it is something non-trivial. And keep in mind, it is a very short period. Okay, so this is the formalism that we were using. Now, for instance, in this listing of Gibbons and Hawking, they propose a number of profiles. And the profile they propose for flyby is the first derivative of this Gaussian. Then they didn't do any calculation in 71. However, with present computers, people who know computers, not my case, but those who can use it, they could find geodesics. This is for the X1, which is the attractive. So an original particle is pushed up a little bit and then brought down to some point. And the other one is that one, and this is the V coordinate, which will play no real role. Anyway, the lesson from these pictures confirms what people, except the Russians, thought as be the generic situation. There is an outgoing velocity. There is no parallel, no motion after the wave passes. The wave zone is here somewhere. Okay, so this is the velocity effect and not the displacement effect. So since I got first access to these results, I have been firmly believing that there was no displacement effect. And Polnareff and Zeldovich didn't give any proof. It may have some historical reasons, I don't know why. Anyway, so what we did was to use a unified framework, which was good for both the usual Galilean aspect and the Carrollian aspect of the symmetries. A unified framework. Basically, the story is, here you have what my friend Duval called Bargmann manifold, is it D plus 2-dimensional. D is the transverse space, U and V are two more light cone coordinates. So the original framework of this Bargmann manifold was to explain basically the Schrödinger symmetry. That means instead of working downstairs with Galilei you work upstairs in one higher dimension, you impose some regulator conditions, and the isometries of d plus 2-dimensional or d plus 1-dimensional manifold will be the centrally extended Galilei group. And then you consider conformal transformations, you pick up 2 more generators which correspond to those conformal generators in the Schrödinger group. So this was the original framework that Duval and company put forward in '84. Actually, much later it turned out that they were not the first. There was somebody called Eisenhardt who published basically the same theory in '29. But Eisenhardt was a mathematician and nobody cared. So Duval and company didn't know about this. They were instructed 10 years after having written their own paper that, oh, look up Eisenhardt's paper. Anyway, so this is the framework to describe originally Schrödinger symmetry or Galilei symmetry, depending if you want conformal or just isometries. So the story is that for the motions, here you have this extended Kauzak line type manifold. This is a vertical direction, which is null direction, unlike in relativistic Kauzak line theory. We project down and you have motions, but these motions are not free. Here they are free. You can even consider massless motions, so light-like motions upstairs. But when you project down, you get a motion in a potential. What kind of potential? Remember that here there is an oscillator. Or you can have more general potentials, basically any potential which depends on the position and u. But well, we are interested in this particular case. Okay, so this is the framework. Null geodesic upstairs project to non-relativistic motions in ordinary space-time. Okay, so this is this Newtonian potential. Here you have a number of early papers, Eisenhardt. There is also a paper of Kim, then Duval and company, and also we wrote one in '91. So my introduction to this whole story started in '91. And this '91 paper has something more. In this, not only the Galilei non-relativistic relation is explained, but there is about Carroll. Why? Because Duval was a joint student of Lévy-Leblond and Souriau. So he knew about the Carroll symmetry and he added a section, but nobody cared for a long, long time about it. It was some side remarks, so who is interested in such non-existing things like Carroll symmetry? Okay, so what are the geodesics? You describe the geodesics, here you have a coupled, I would say, oscillator equations, but one of them is attractive, the other one is repulsive. And that is also for the V. It is much more complicated. So should we solve it? The answer, no. Because it is just the horizontal lift of the motion. So if you have, once you have the motion in 2 dimensions, the third dimension, which is the internal dimension in Kauzak line, is just horizontal lift. So you don't have to take care of this. By the way, for these people who work now, so much interested in fractons and so on. So this is what corresponds to this fracton direction in the decomposition. Okay, so we are interested in this particular case. So it is a repulsive and an attractive harmonic force with a possibly time-dependent frequency. Now, as you know, this is a huge difference. If the frequency was constant, then you would learn in high school how to solve it. If it is non-constant, it depends on time. U is here, time. Then you are lost because it's a Sturm-Liouville problem and you have no general solution. except in some very particular miraculous cases with a lot of work. So it is somehow from very simple to very complicated technically. It can be treated perfectly numerically, but you see, for me, I need somebody who does the numerical work. I am not able to do. I was the worst student in numerical things when I was a student. So the example first, take the simplest possible, a Gaussian profile here. So this is a Gaussian function. Here you have, so this is basically the wave zone here. It is 0 before, 0 after, and here there is a kind of burst of gravitational wave. This is the simplest one, not a realistic one, but the simplest one. So this is the simplest case which can be studied, and it was the starting point of Gibbons and Hawking. Now you make the picture and you see, in one sector, it flies away madly, diverges, because it's repulsive. The other, it is focused because it is attractive. And then there is the V component, which is, as I told you, not so much interesting. It is a consequence of the first two. So the question is, what about displacement effect? These plots show that there is no displacement effect. And I have been firmly convinced of this until recently. Just a remark. Here I will concentrate on two cases. First of all, the simple Gaussian, just as a toy examples. And then I will discuss a little bit the flyby. But there are higher derivative possibilities for other more complicated situations. It is a full list in the original paper of Hawking and Gibbons, and we also wrote quite a long paper about soft gravitons, which contains a lot of details of how to do. So now the question is, the problem we cannot solve the equations of motion for this exact plane waves. What can help you? Either one of your favorite gods or a symmetry. Since, well, the symmetries were identified by Bondi, Pirani, and Robinson in '59. As I told you, two obvious translations, and then two which have never been identified what they wrote. It's not true. They were identified by Souriau, but nobody knew about Souriau's work. He was so careful to hide it that nobody knew. So anyway, this was the miracle that Souriau found a solution, not knowing much about the standard knowledge of Bondi, Pirani, Robinson, and so on. And the only person who knew about it was Duval, who was a joint student of Souriau and Lévy-Leblond. And he sent me a mail. Look, what Souriau found is basically the same as the Carroll transformation of Lévy-Leblond. And then we jumped at it and wrote a paper which has some success about the Carroll symmetry of gravitational plane waves. What we found corresponds to this, what people call dipole symmetry. What people call Carroll symmetry is the dual of it in another direction. We didn't know about the dual at the beginning. We knew about the vertical one, which is now mostly called dipole symmetry. We called it Carroll because it was the Carroll group. Okay, so we gave a full picture that I will now, because time is getting very short, so I have to accelerate. There is you see, Duval was a mathematically minded physicist. So he had some very rigorous geometric definitions, how to define all these isometries. But, well, this is the picture. The restriction of the Barman space to a vertical slide, that means fixing time. This t is the same as the u because I didn't update my slides. So this is the same. It is a U constant. You take this slide, it will be a manifold. Here, d dimensions in space, and one more dimension, which we call Carrollian time. Usual time is t, non-relativistic time. It is another vertical time, Carrollian time. And then the question is how to describe geodesics in this place. So the answer is found by Souriau, or used, I don't know how, because he never told where his ideas were coming from, to code Baldwin-Jeffrey-Rosen coordinates. That means, remember, in Brinkmann coordinates, here it is flat, but here you have a coefficient of du squared, which is the potential. And these BJR coordinates, everything is put here. There is a U-dependent, non-trivial 2x2 matrix here, but there is no coefficient of du squared. And Souriau used these Baldwin-Jeffrey-Rosen coordinates, which were very useful. However, when they were introduced, they immediately provoked a debate which went on for 50 years. Can gravitational waves exist? Because these coordinates are singular. So it can be proved these coordinates are never global. You start with a completely regular situation. After some time, it will become degenerate. So a real situation for a gravitational wave cannot have singularities, so it is unphysical. Rosen, for instance, never accepted that gravitational waves he predicted would be real. Einstein was not a fan of it. He was hesitating and so on. He withdrew a paper because they criticized it and so on. Okay, so what are the isometries? And this was a real genius of Souriau. He thought, look, you have BGR coordinates, and you implement a 5-parameter group in this way. So this C is a translation. This is a translation in a vertical direction. And here you have age of U, which acts on B. What is age of U? He gives a rule. Take the BGR profile, invert it when you can. When you cannot, of course, it's finished. When you can, invert it. Integrate by U, you have here a 2x2 matrix, which is a function of U. And here is the coefficient which will implement boosts. So for instance, if you have identity, which is the simplest empty case, just Minkowski's case, this age is nothing else than U minus U0. And you pick up Galilei boost. However, in a more general situation, you can implement the following. You can, well, here I think I have to hurry up. You can do the following. You can implement for a simple case with age U equals 0 on the 0 section, which is a Carroll manifold, and then you have this action, and that you know. This is what Duval has seen and sent me a mail saying, oh, how funny that these two people who didn't speak to each other did the same work long time ago. However, if you go to another slice, you see, this is Carroll slice is not unique. You have for every fixed values of the U or T parameter. Every vertical slice is a Carroll manifold with the vertical direction as Carrollian time. But they are not the same. They are related by what? By this age matrix. So this is what does what you want to do. And then you recover Lévy-Leblond's formula for a Carrollian boost. X is fixed, but the Carrollian time is moving by a boost. Okay. And this is in the 65 paper of Lévy-Leblond. That time he was in his early 20s or so. An amazing person. But it was recognized just some time later in 2017 by Duval. So the united framework is the following. Here you have this Bargmann manifold, which is D plus 2-dimensional. D dimensions are transverse space. U is Galilei time, V is Carrollian time. So the restriction to this vertical slice is Carrollian physics. The restriction, not the restriction, the projection to this with coordinates U and X is Galilei space-time. You know, Duval was a very mathematically minded, so he preferred Newton, Cartan, and well, it is just a complicated way to say things. So this is this unification of the two behaviors. Okay, now what are the geodesics? And this was the problem which could not be solved for I don't know how many years. And the solution is quite obvious. Once you have these symmetries, you have 5 symmetries, you can integrate the equations of motion. And here is the answer. X of u is age of u, this 2x2 matrix, which I called Souriau matrix, because I have never seen it before, and Souriau put it into his conference proceedings. It acts on the momentum, and you can also shift with k, and then if you lift it here, you have one more generator for vertical translations. So in Flat-Minkowski's case, it is just the usual Galilei free motion. But in some complicated case, when the profile A, you know, because age is the integral of A minus 1. A is the 2x2 matrix coefficient of X in Rosen coordinates. A minus 1 is its inverse here. And then age is what it is, a 2x2 matrix you have to calculate when you are given A. So you use here the A equal 1, you pick up usual Galilei transformations. If you have some more general, then you have to find it. And the answer is, for instance, for this third derivative which, of the Gaussian, which is called the gravitational collapse profile by Hawking and Gibbons, it starts like a Galilei. Here arrives the wave. There is a lot of singularities and jumping up and down, and then very quickly it dies off and becomes 0. The boost acts trivially, no boost. So this is just a complicated example, which goes a bit outside. Now, what is interesting is that formula. You can use it if you have the age of u. Then you apply this formula. What is the simplest age of u? It depends. But what is the even simplest case? When the original momentum is 0, because then this whole term is switched off. And you have xu equal a constant. So this was the amazing situation that we found by that time with Gary-Gibbons, and Duval didn't want even to accept it first. If you have initial no velocity, and this is a conserved quantity, so it remains with no momentum, then you will have just fixed x and a vertical motion along a line. This is the Carrollian time. So this was the amazing surprise that you see these motions which were obtained in Brinkmann coordinates using very complicated numerical procedure. So you can see it is not a joke to obtain this. They are actually images of x0 equal constant by this PU matrix, which is related to the Souriau matrix. So once you have the Souriau matrix, you have all the complications. Otherwise, you have in BJR, you have just trivial motion. And every complication comes from this P matrix, which is the square root of the A matrix and so on. So, okay. Now the question is there a displacement effect as pretended by Zeldovich and Polnareff? And until very recently, I was certain it was not. These were our pictures. However, there is a miracle. My friend P.M.Zhang in China, he is very good at computers, and started to play with the coefficient and found, for instance, I will go directly to the flyby. So he found that playing with the coefficient, the amplitude, and the damping of the, somehow in a very complicated relation. You see, lambda is 0.5. But he was playing with k, with the amplitude. And he found that if we fine-tune this, then an incoming motion will go out with no velocity, and also for the other components, because you have two components. So you will have memory effect, pure displacement effect, if you choose smartly these coefficients. He found it completely numerically by playing with the computer. Now, what is interesting in 2 dimensions, the projection to 2 dimensions, you can consider energy. And the energy at the beginning is 0 because it comes with no velocity before the wave arrives. Then it picks up a huge peak of energy, but then it decays to 0. So an incoming wave will excite your particle, but the particle radiates out all the energy and the wave continues without energy loss. And this may be a miraculous situation. Here are some illustrations how it goes. For instance, the transverse energy, usually there is a loss. Here there is 0 for this first value. Here there is again a 0 for the second value, and so on. It is now our philosophy, which is for the moment speculation, but we hope to be able to prove, with these values, you have velocity effect. But velocity effect means losing energy. When these waves come from millions or milliards of light years, they lose, at the end they get dissipated. What are the waves which do not get dissipated? Those which do not pick up energy. So these are these particular values which are interesting. And this means what? It means that, for instance, you have standing waves in the wave zone. And then the speculation is here. In the velocity memory effect, the particle picks up some energy. Tiny as it is, it must be taken off from the waves. So since the distances are so huge, the wave has to cross dust and galaxies and so on during these millions of years, and slowly gets dissipated, eaten up by the dust and these obstacles. With the sole expression when there is miraculous constellation, when the absorbed energy is radiated back. So the wave doesn't lose anything. And these are what we could come, and this is no energy loss, and the wave propagates at long distances. So our hope, nothing certain, our hope is that these non-dissipated waves are that people can observe now using this huge equipment of 5 kilometers for LIGO or 5 million kilometers for the next project and so on. So, well, this is a speculation that we have to check with those who do the observations and understand their work. Thank you. Oh, sorry, I have to come close because I am deaf and
Maybe just a curiosity. There's also like an analog of this memory effect.
well, there is something similar, but it is a purely gravitational aspect. But there is, of course, there is a good analogy with the electromagnetic case, but that we did not study.
No, I was asking what are your thoughts on like how that will be easier or
Well, in some sense, there should be zero modes. Yes, because these are, when you don't lose energy, that means it is a zero mode, basically. So it between the radiating away or absorbing everything. So it should be somehow in the limiting case between the two, which is very seldom. You can find one in every, I don't know, thousands of values. But you don't beat me.
No. In the Carroll case, we know that there are also tachyons that move.
Yes.
Is there a possibility of using these?
Well, we didn't think about it, but it's a very good question. Because the problem is how does this energy first absorb and then radiate back? So maybe the tachyons may be another example which could help to understand the physical process. So I think it's a very good question. So please refer to our work when you write yours. Sorry. Yes. Yes.
Is non-linear memory effect.
Well, our theory is a linear theory. Christodoulous is a non-linear theory. Now, the problem is that I believe, at least, or hope, that in this simple case of basically oscillators, so gravitational waves which are oscillators, it might be justified not to consider the higher order terms. I don't know if this is true or not, but this is the hope. The basic difference that this theory I could understand, and the paper of Christodoulou I could never understand. Well, it is not his fault, it is my fault, but you see, when I will be grown up, I will read it. But that's a good question, actually. Sorry?
In which sense what you describe is linear theory? Or linear effect?
Well, the profile of the function is just a harmonic function with a time-dependent coefficient. So this is maybe, if we are lucky, this may justify not to consider higher order terms. I don't know. I have no, that's a hope. But again, it will be very interesting. You see, when we submitted our paper, it was the question, basically the same question of the referee. And then we had to say, look, we don't know how it happens. I asked Gary Gibbons, which usually when I don't know something in relativity, which happens very often, I asked Gary Gibbons, who knows everything about general relativity. And he told, I never understand this paper of Christodoulou. Then I gave up. So, yes, you had also a question?
No, I was just pointing to.
Oh, I see. I just wanted to comment that here there is m. It means that counts the number of half waves in the wave zone, which turns out to be an integer. So it is a kind of quantization of the possibilities depending on the wave. And we are desperately trying to find some formulas for it which are analytical. In the simplest case, which is in one dimensions with the square potential, we have an explicit formula that the area below the curve multiplied by the wideness, width, is a multiple of pi times an integer multiple of pi. So we have the picture. I skipped, unfortunately. Here. You see, this area should have the form, h is basically the height, and the area should be an integer multiple of 2 pi h. So this is a constraint. Here you have 1/2 wave, you have a full wave, you have, well, this is the full wave, and here you have 3/2 waves, always an integer number of standing waves. But this is a particular case, and we are not, I was hoping that my friend Paming will send me a general picture, but it didn't arrive this morning. So